There are just a few things that I want to do today. My plan is to get through those things, which is really just a bit more on Glog, then Word to Vec and retrofitting. And that kind of rounds out this first big unit on distributed representations. Next week, we're going to turn to the topic of supervised sentiment analysis and explore a different set of topics. My ideal for today is that we get through this stuff. We're not in a rush, so feel free to ask questions. But when we get through it, we're just going to break. And I'm going to encourage you to do some hacking, to explore the notebooks if you haven't already, to get a more hands-on look at the material. Or also, you could just dive into homework 1. You should certainly make sure that your system is set up. Please don't leave here today without feeling like you're ready to just work productively on the problems. So a bunch of the teaching team are here in the room, and then we're going to have a setup. I'll give you the details on that later, where you could video in to talk to some of the TAs who are going to be available in a kind of queue. So if you're not in the room right now, but you need some help, feel free to contact us. And I just want to emphasize that this is the moment, the best moment to get your system working. Do not wait until Monday afternoon to discover that you don't have crucial components. That's what this is the perfect moment to make sure that's all straightened out. Before I dive in, any questions or comments? Yeah?
There's 2 office hours tomorrow. One of them says that it has a Zoom, the other one doesn't. Do they both have are they both also online?
For tomorrow.
Does it matter than an evening?
That's right. He's kind of always by video.
Oh, okay.
To reach him. And I think flesh and blood creature. Basement. So you could choose either one.
Can that one also be online, or is it only?
No, that one you have to go see, right?
Yeah, but if you want to call in, we can arrange that.
Oh, okay. Thank you.
Yeah. Yeah, you could, I don't know. Yeah, you could, I don't want you to email me directly, but maybe you could post on Piazza. Actually, that would be tough too. Maybe I'll just create a link, so if people want to call in from mine, they can as well. Just so I'm inclusive of everyone, whether they're a person or not.
Okay. Do what you can, but otherwise you might have to make your way to
Do we use Q status?
We do. That's what we're using today, right? Yeah.
No,
No?
not in the Zoom today, because we have the similar system in the Zoom.
Okay. Yeah, so we use Zoom somehow. Can you give details on it when we in the middle? On how it works? Yeah.
It's very easy. You just basically call in, and then it appears, for us, it appears in a queue. I think you are not going to be able to see the queue, but we see it.
Okay, great. Where we left off is that I had planted the seed for Glove. Basically, I said some nice words about this paper. I'm a big fan of this paper. And I gave you the intuition, and also here's some other practical details about implementations that you might use. So we're using mittens by and large. There's also a C implementation, and I think in a minute I'm going to show you kind of a reference implementation that is very, very slow, but it's kind of what you would do to just naively implement the algorithm, and I think that there's a real pedagogical value to seeing exactly how those computations would go. So we're going to glance at that, but I'm not saying that you should use it for anything beyond study. So here's how I introduced Glove. I gave at the top there what they present as kind of their ideal objective, which is that for row representation, or a row embedding W sub I, it's dot product with a column embedding W sub K. That's the primary term, and then you have 2 bias terms. And the idea is that that should be equal to the log of the co-occurrence probability, or at least, I guess, proportional to it. They kind of dive down further, so their ideal reconstruction of what that dot product is that it should be the log of the co-occurrence probability. And they define that co-occurrence probability as the log of the co-occurrence count minus the log of the row probability. And if you do allow that the rows and columns in this matrix might be different, so you'd want to not just concentrate for normalizing on that row, but also on the column, I think you get this expression here, which isn't in the paper, but I think it's certainly in the spirit of the paper, because even for their matrices, the rows and columns could be different. And so then you've reconstructed the co-occurrence probability as the log of the co-occurrence minus the product of the row and the column. And what I just pointed out to you is that, that's PMI. that is certain, like in some sense that's the literal calculation of PMI. And you can certainly see that what we're getting from this picture is that Glove is built on that PMI intuition. It's not the same as PMI, of course, because we're learning regularized, reduced dimensional representations, whereas PMI is just a reweighting of the entire count matrix. But I really like this as an entry point to Glove. When you think of Glove, you could think of it first and foremost as capitalizing on that core insight. That's where we left off. There are a few more details for the paper, though, that I think are really important for why Glove works so well. So again, I've just repeated the original Glove objective up here at the top. What they actually argue for is a weighted version of it, which you see down here. And the new piece is, like, at its core, you have that dot product again of the row and the column. You have two bias terms for the row and the column. And then you subtract out the log co-occurrence. It's additionally weighted by this function f. So f is a function of the counts. And what it's doing essentially is kind of flattening out and rescaling those count values. So f of x, it's the general function defined here. You set x max, the default in the spirit of the paper is to set it at 100, so a count of 100. So if x is less than that max value, you set it as a proportion of that max with an exponential scaling here of alpha. And if it's equal or greater to the max, you just set it to 1. And yeah, as I've said down here, alpha is typically 0.75 and x max is typically 100. I think that's fine, reasonable defaults. I'm going to suggest that you think a little bit about that, though. But is that clear so far? That's kind of the whole model, right? When you think of Glove, you should think of that dot product of row and column with some bias terms, and then subtracting out the log co-occurrence. Make sense? Plus a reweighting of f. The Glove hyperparameters. So there are really three. The first is just the dimensionality of the learned representation. You get to set that. You can set it at any number, and you can imagine that setting it at larger values is going to give you more capacity to learn, but also take more time and everything else. So that's kind of something that you play with for all of these models. X max is going to flatten out all the high counts. And the idea I want to plant there is that you might reflect on that value. And the way you might think about it is, for my count matrix, what percentage of the values are actually at or above that threshold? If it's 100% of them, for some reason, then picking x max to 100 is going to turn your entire matrix into a bunch of ones. That's certainly not going to be good, right? That's unlikely that you would have a count matrix that was that dense. But what percentage is it? And what are you doing to your matrix when you flatten out maybe what's a large percentage of the values? So you could think about that. And then you could also think about alpha, which is going to control how much scaling you do for counts that are below your max. And here I've given an example. So the incoming row vector for this f I've defined with the defaults is 100, 99, 75, 10, and 1. And once I've applied this reweighting, it looks like this. So obviously the magnitudes are much different. 1, 0.99, 0.81, 0.18, and 0.03. So you're doing something very important to the space when you do this reweighting. Make sense? This is a new slide that I added. I recognize that it's very dense. It's kind of there for a reference, but let me give you a guided tour of it. And let me step back and just say, I was thinking about other ways that we might, at an analytic level, get a deeper understanding of Glove. We have the PMI insight. I've shown you the Glove objective. But what else could we do? And what I thought is, when I motivated LSA before, I gave you this example of gnarly and wicked. And my motivation for showing you that was, these are two words that are similar in semantically. They're both kind of positive slang terms, maybe. But they're unlikely to co-occur with each other because they're kind of from different dialects. That was the idea. And my pitch to you was that LSA has the capacity to recognize that they are similar, despite never co-occurring, because they have other neighbors in common, because they over-occur together with awesome and less than you would expect with terrible. And as a result, LSA is able to capture that insight, right? That was one of the motivations there. And I thought, how does Glove do this? Because Glove, by its nature, because of this log count thing here, it doesn't even visit zero-valued cells. Yeah, this is like my just very quick reference implementation, where you set up the word and the context matrix and the bias terms. You can take the log of the entire matrix all at once, so do that as a pre-computing thing, and you could reweight the entire matrix in the way that I just showed you with F. You can do that outside of the loop. And then once you start iterating and working on specific examples, you don't visit the values that are 0. And the reason is because of that log thing, right? You would either have a problem there, or you'd want to be able to say that this is just, the value is 0. There's no update for this example. So that's a kind of a definitional thing about Glove. But then, how is it going to do what I wanted? In the case where, here's my count matrix, I've said that wicked and gnarly never co-occur. This is a version of that LSA example, but I made it word by word because, of course, Glove requires a word by word matrix or a square matrix. So how is it going to do this? I kind of hope that it does have the capacity to do it. Actually, does anybody have any guesses? There's a lot of detail here, but like, what's your hunch? Anyone have a hunch about how it might be able to do this, or maybe it's going to be unable to? Yeah.
Basing it on the relation to the word terrible, which is a negative term, so how the positive nature of it is connected to the negative words.
Yeah, beautifully put. That's in fact what happens, I think, experimentally, is that what Glove do is push both gnarly and wicked away from terrible and toward excellent, because it does have co-occurrence values for them. And you're kind of relying on its ability to do that in order to achieve this abstract connection. And I think that does happen. So what I did for this little problem is I just got rid of the bias terms so that I could display the calculations. And I also started the Glove optimization process in a way that I was sure that gnarly and wicked were really far apart. So at iteration 1, I basically made them to be completely separate parts of this space. And then I thought, what's going to happen as I do these updates? And building on exactly your intuition, what I decided to do is look at what's happening for both of them as it relates to excellent. And I could have done it for terrible, where you'd expect them to push away. And I thought that might happen, that they both gravitate toward excellent. And it does. So here's, it's kind of small, but this is wicked and terrible and awesome and gnarly. And that's what I meant, that gnarly and wicked are at like opposite ends of this little two-dimensional space here. And after one iteration, it really has been reorganized. Here's awesome, here's wicked, and here's gnarly, and terrible has been thrust up into the corner here. And I think if I keep running this, then gnarly and wicked are just going to gravitate closer to awesome and farther away from terrible. And that's the sense in which we'll be capturing their abstract similarity. And then on the right here, what I've done with kind of color coding is just make that really concrete. So there are the counts up in the upper left. This is the reweighting. This is W0 and the context vector 0. So that's the starting point. And I'm watching for gnarly and wicked and how they're going to get closer to awesome. And when you do that calculation, this is just the derivative of the Glove objective here, which I stated up in the corner. You get these error terms. And then that updates the weights. And then after another iteration, the error terms have gotten smaller. That is, just as you see in the picture over here, these terms are gravitating toward excellent. And you can imagine that as I go, these values are going to get closer and closer to 0. So I don't know, I found that reassuring. Does it make sense? Any questions I can answer about it? Yes?
Do you mean awesome or excellent?
Awesome? That's the one that I picked. Oh, I wrote excellent up here? I did mean awesome. Yeah, this is my space. Gnarly, wicked, awesome, terrible. And I set it up so that awesome is really frequent and co-occurs a lot with both gnarly and wicked and hardly ever with terrible. That's the idea. And then you can see it pulling toward the blue. Those are the comparisons I keep making. And just for the comment before, if I had done comparable comparisons with terrible, I think I would have seen them pull apart.
Why would gnarly and awesome have like a lot of co-occurrences?
They have none. Gnarly and awesome?
Yeah.
Oh, because they're both positive slang terms.
But if a co-occurrence is like right next to each other, I'm trying to think sentences.
Oh, this would be like if I was reviewing your paper and I liked it, I would say it was both gnarly and awesome. I don't know. Probably that would be for more like your skateboarding moves
I see.
than your paper. There was one more thing just to kind of fill out my little analytic framework here. So when I showed you all those reweighting schemes before, I showed you before and after on the distribution of values. And here for Glove, this is really nice looking, right? So the raw counts come in and they have this really difficult scaling. And then when you reweight with Glove, that's just raw counts coming in, you reweight and you get this like completely normal distribution here of cell values. And look how nicely they're scaled between -2 and 2. And we'll see this, I'm going to return to this point again and again, like a lot of the deep learning models that we look at are going to be very sensitive to the scaling of incoming values. And you could just say like this is a really nice starting point for a lot of those networks because everything is kind of scaled in a rational way. So this is also partly why I think Glove does well as an input to another system. And then I had some Glove snippets here, just showing you how to, first what I did is just load in the data frames, 2 of them, IMDb5 and IMDb20, and I just wrote a little function that would look at the number of non-zero values that were below some threshold that I set, so that would be X max. And for IMDb5, it's about 2% of the values, and for IMDb20, it's 15% of the values. Corresponding to the fact that IMDb20 has a much larger window, and therefore it's much denser because more things co-occur with other things. But you can see that that is interacting in an important way with the chosen value for X max because I've done relatively little to IMDb5 by thresholding, but I did a whole lot to IMDb20. I really made a lot of those values the same, even though they might have been very different. So something to keep in mind as you use Glove that you might, I think I should have been more reflective on this in the past when I've used Glove to think about the impact of that hyperparameter. And then for this code snippet here, what I did is just test this idea. The Glove objective is to learn word vectors whose dot product is proportional to their co-occurrence count. And so you might think that if I can somehow perfectly achieve this objective, then I'll get a perfect correlation between the dot product for 2 vectors and their co-occurrence in the original count matrix. So I just wrote a little function correlation test that does that. And I ran Glove for a little while. And you can see that the correlation is about 0.38 for IMDb5 and about 0.48 for the IMDb20. For the amount that I ran Glove, I would expect that value to get larger the longer I ran Glove for. But this is a kind of measure of how much we're living up to the Glove objective and also kind of how much we're compromising on the original count matrix. It's not that we want to reconstruct the original count matrix, so maybe some loss is useful actually. Yeah?
Did this slide change from the prior PowerPoint?
I made just one change. I meant to do a shout out for that. Somebody noted that I had taken the log twice. It doesn't matter whether you take it in the line row prob or row log prob, and so I just did it on both, which was not good. It was affecting the scaling, and since the correlation test that I chose is sensitive to the scaling of the values, the original correlations were much higher. And I should have been reflective. They were so high that I was like, can that really be right, that it's doing so well? This is much more realistic. I thought I would do one more model here, word to vec. I'm just going to do this one quickly, and I can justify that in part by the fact that the Tensor Flu tutorial on word representations, vector representations of words is basically an introduction to word to vec, and it's really, really good. So that's my first practical tip, and the other is that if you want to train your own word to vec representations, then GenSim is a nice Python package, kind of arbitrarily scalable, that you could use to do that. But let me just give you the gist of this so that you have it in your toolkit. So the fundamental idea that I take it for word to vec is that I can take a corpus and think of it as a labeled data set. And the way that I can do that is by setting a window size, just the way we did for all our count matrices, and think of pairs of words that co-occur within that window as labeled training instances. This is a positive label that because it was is there in that sequence, then I say it is labeled with was. And I also say it is labeled with the, and so forth for all of these co-occurrence pairs. So it's a funny kind of supervision, right? It's not, but it's like a positive example of this word co-occurring with the other one. That's the sense in which this is a label.
Where do it and the co-occur?
Here.
It's window of 2, right?
Yep, 1, 2. Yeah, so it and best do not co-occur because they're outside that window. But that's a parameter that you would set, and the larger you set it, the more training data you have in some sense. Of course, it's not all equal. So this is the basic model, and you can probably see at the top here that this is a kind of log linear or softmax classifier. You might have seen this equation before. This is the explicit objective, but I think we could reduce it all the way down to this kind of learned model here where I have X is my embedding matrix for the vocabulary, W is some weights, maybe we also have a bias term, and then the kind of hard thing to get used to about this model is that C is a label vector for an individual example, and it's one-hot encoded, but it has the dimensionality of your entire vocabulary. If you have 20,000 words in your vocabulary, then it's a 20,000 dimensional vector with a single word having a single dimension having a 1, corresponding to the word for that training instance that co-occurs with your input word. So this is obviously really difficult to train, and it's quite slow, but that's the intuition, right? Is that I created this labeled data set, and then I just do a very standard thing in machine learning, which is have a classifier that learns to predict those labels. It's just that it happens in this very high dimensional space. And I take it that that's kind of the core insight behind what's called the skip-gram variant of word-to-vec. And then one other thing you might think about is I can do this for individual examples as they come in. But if I do it for my entire vocabulary all at once, that's fine because they're kind of all independent. But when you phrase it that way, you start to see that this is kind of like another one of these matrix factorization methods where I have like my word vector or my word embedding space, and I have my context embedding space W, just like Glove did, and I'm taking all those dot products. And the objective of the model is to push those dot products in a particular direction. And in this case, it's in the direction of favoring the things that co-occur a lot, and in turn disfavoring things that don't co-occur a lot. In practical terms, I think people don't use this model because of the very high dimensionality of C, causing lots of problems. So the more popular version, which is implemented for you in Tensor Flu, you'll see that in the tutorial, is called skip-gram with noise contrastive estimation. And this is a kind of approximation of that model that I just showed you, where instead of doing that very high dimensional thing, I have the sum of two separate objectives here, each one of them binary. And it's just saying for the left here, those are the things that actually co-occur, push in that direction. And then I sample some negative instances to be the negative ones over here. And they give some advice about how to sample negative instances, but those are presumably things that you didn't see co-occurring in your training data. It's not that they never co-occur. It's kind of a miracle that this works at all because, of course, they might be perfectly well-formed pairs, but the idea is that on average, with a large corpus, when I sample these negative instances, they will be kind of sequences that are unlikely to appear together, and therefore it's right to downweight them. Yeah?
Is there some intuition that you would want to choose negative pairs that kind of could appear, though, or should you just pick kind of totally absurd pairs?
That's an interesting idea. It sounds like something like a linguist would suggest, which is let's think very carefully about which words are plausible. I think they don't do that. They have some schemes for sampling from the frequency distribution, which might kind of align with your intuition. But I've not seen work that tried to get down to like, can this adjective appear next to this verb or not? Anyone seen anything like that? It's a potential place for innovation just because this negative sampling part really does matter for how efficiently these models train and what kinds of embeddings you get out. Okay, final section here, retrofitting. The spirit of this is, I think it's very exciting to study distributional representations, and I think they've been very successful. And it's kind of amazing how well it works given that they operate only on co-occurrence statistics in large data sets, in large corpora. So obviously, there are important aspects of meaning that are latent in that co-occurrence data. But I do not myself believe the claim that that's all there is to meaning. Right? If I think about meaning as it's studied by linguists or by cognitive and developmental psychologists, they emphasize other things beyond co-occurrence, like grounding in a social situation, interaction with other people using language, all of that stuff that's not merely co-occurrence, but rather about kind of our entire cognitive lives. And that leads me to doubt that these distributional representations are going to tell the whole story of meaning. And a response that I really like about that is that we might look to ways that we could take these distributional vectors and improve them with some supervision. That is, imbue them with information that wasn't merely co-occurrence information. That's the pitch of retrofitting, and it's really just one of many methods that you could adopt for doing that. Yeah, I've given a kind of summary. I like that these things are high dimensional. I like that they're dense and capture lots of linguistic relationships, but I'm doubtful that we can capture meaning solely from co-occurrences, and I don't like that there's no grounding. We can leave the symbolic question for later. I'm not sure I have an opinion on that. But these two things are things that I would really like to address. There have been in the past a bunch of different ways to do this, a bunch of models proposed. This is some work that I did with Andrew Moss when he was a PhD student here. And this was really just taking distributional vectors that were learned from a kind of autoencoder and infusing them with sentiment information, like with the gradient information from a sentiment classifier. And what we're pitching here is that you could take this space that's kind of not well differentiated when it comes to sentiment, as you can see by the mixture of colors, and kind of really spread it out so that the negative and the positive are in their own regions. And that's coming from the supervision. And there are lots of ways you could do that. Here's another example. This is actually some stuff that I did in an exploratory way with Moritz Sudhoff, one of our TAs. Like here I have a kind of PMI space, and if I take that space and train it against sentiment objective with a deep classifier, and I look at the hidden representations from that classifier, they, of course, have shifted the space around in response to their supervision. And you can see a really deep sentiment split here with all the positive and negative words really gone into their own part of the embedding space. These methods can be kind of hard to tune, so I was really excited when I saw this retrofitting model appear. This is from Faruqi et al. It was a NACL paper, I think one of the best paper awards at NACL. So kind of pioneering work. And it's implemented in the notebook in case you want to explore it. I've showed you how to experiment with WordNet and so forth. The gist of this is, here's the objective. And what I've said here is that this is an objective that's balancing two pressures. First, I want to be like the original vectors that I've got. That's the pressure in orange. But I would also like to look more like my neighbors in a knowledge graph. Let me unpack that a little bit. Let's suppose that you trained a bunch of representations by whatever method. So you have some vectors for a vocabulary of English. The sense in which you're retrofitting is that you could find all of those words, say, in the WordNet graph. Just look them up. And now you could imagine that those nodes in that graph are actually your vector representations. What the retrofitting model does is say, try to remain like those original vectors, but also update them so that they're more like their neighbors in the knowledge graph. And that's the sense in which you're retrofitting. And it's kind of nice and modular because you can take any embedding space, and as long as you can ground it in some kind of graph, you can run this objective and move those vectors around. So here's a quick example. In this tiny little graph here, this node 0 is related to 1 and to 2 in the unidirectional faction. When I run retrofitting, you can see that 0 moves closer to both of them. And they stay put, 1 and 2, because they're not related back to 0. It does matter which direction they go in. Here's a case where they're all related to each other. And what you can see with retrofitting is no matter where they start, they're going to kind of pull together because everything is, by this graph, similar to everything else because of its connectedness. And then here's one more example. I meant there's a hyperparameter alpha and beta. And if you set alpha to 1 and beta to 1, then they're evenly balanced. Suppose I set alpha to 0. That's a kind of interesting edge case where I say, I don't care what the original embedding was like. All I care about is being like my neighbors. And that's degenerate, right? Because very quickly they just become identical to each other with alpha at 0. And conversely, if you set alpha really high, then you'll really remain like your original representations, and the graph will have almost no influence. And between there, you might find something that's kind of usefully making, using the original embedding, and also making use of the knowledge graph structure. Yeah?
Where is this knowledge graph structure? Like, where does it come from?
You need to have it out there in the world. So I gave the example of WordNet. This is a case where you have really easy alignment between whatever representations you've trained for words in English and this pre-existing structure. But you can think really creatively about this. Lots of data can be represented in a graph, and if you can find that structure, then you can perform the retrofitting step. And I've given some extensions here. One thing that you might find unsatisfying about the original retrofitting model is that it's baking in very deeply the idea that if I'm connected in the graph, it means that I'm like my neighbors. It's like a one semantics for these things. And this is a bunch of attempts, I was involved with some of this work, to relax that assumption. So for example, in WordNet, there is an edge relation for antonym. And I think it's probably a mistake to say that just because I'm connected via that edge, that I want to be similar to that word. Antonym has a very different semantics from, for example, synonym, which is a dominant kind of edge, or hypernym, like entailed or entailed by. So these are nice extensions, and we released the code for this middle one. This is kind of the most general version of this that would subsume this other work that was more specialized around different graphical relationships. And then here are a few code snippets. I'll let you look at the notebooks for the full story because there's some data processing involved in, for example, using WordNet for retrofitting. But here I just gave a simple example that kind of documents the interfaces so that you could think creatively about applying it in a new domain. That's it. I hope that's an inspiring idea to end on. Yeah.
Could you, in order to construct the graphical representation, just take like any set of embeddings and then just sort of do like a choose k closest neighbors and then artificially form a graph that way and then run retrofitting on it?
Oh, interesting. So you would say from the original space, connect things that are close by some standard and then retrofit to them. I mean, you could certainly do it. It's well defined. I guess I don't know what would happen. I guess what you'd be saying is that for whatever threshold you set, you really want those things to be pulled together. And then everything else should kind of drift into the background. It's unusual because I think of retrofitting as, I have my embedding space and I have some other resource, some other knowledge graph. And you're kind of fusing them together. I don't know, but you could try it out and see what happens. Yeah?
What does retrofitting with WordNet do to the analogical relationships? Does it preserve those things or make them better, destroy them?
Oh, that's a good question. Well, so in the original paper, I believe they test on analogies and see some improvement. I think that's one of the tasks that they evaluate on. I should double check that. They retrofit to WordNet and FrameNet, maybe one other graph. Oh, and also a data set of paraphrases. But I forget precisely the experiments. It's an empirical question. I would check the paper. Yeah.
Like model ensembling, does an idea of word embedding ensembling can work better? Like some case like word to vec and glove, like some kind of a weighted ensembling of both of these can improve the embedding in general. Like, does this idea hold in strength?
Are you trying it for the bake-off?
No, I just.
Yeah, the question was basically whether or not you could combine forces, that is, bring a bunch of different embedding spaces together and see some gains. I think the general answer is yes. And the thing you might think about is, what's the overall scaling of the representations that you're creating? Are they kind of harmonized, or is it obviously just two things that you smush together? And because that's going to affect how easy some like later learning problems are, for example. But I think the general answer is, yeah, pull these things together. If you look at recent papers that use these newer contextual word representations like BERT and ELMO, you might notice that in a number of places they have actually included the Glog vectors as well, to have even more dimensions and even more information brought into the problem, and you see gains in that case. And for the bake-off, it's certainly within bounds to smush together all four of those count matrices or things that you've done to them and see whether that leads to improvements. And that's a nice transition point. So what we want to do now is break, no more lecturing, get hands-on, make sure you can get through the homework, because I think those are nice preliminary steps to building your own system. Build that system, and then you have a bake-off entry ready for when we do the announcement on Monday with the new test sets. A few tips. Thank you again, in the back somewhere. We added to utils a function called fix random seeds, and you have a bunch of options for setting random seeds for various parts of the scientific computing environment that you're in. You might want to do that for your bake-off entry as a way of ensuring that we can exactly reproduce whatever you got. And then we could have a separate discussion about whether if your win depends on seed 42 and you don't win with seed 1, what that means for us, but let's not dwell on that now. You might make use of this function in utils to make it easier for us to reproduce exactly what you saw. And that is allowed. The bake-off is, of course, oriented towards the best performing system. That's the standard thing for bake-offs. But in talking with you, I have become interested in two other questions. Definitely, what's the worst performing but well-motivated system? We were talking about this yesterday. So not just the worst performing system in general. That's not so interesting, because you could just do a bunch of incoherent stuff. But like, what's the system that really ought to have worked if you think about the theory, that was a disaster for the problem? I really would be interested in seeing those systems. And this is a kind of grim joke, but which systems consume the most resources? So you can see on Piazza that somebody did train Glove for 50,000 iterations, 19 hours of CPU time, and it didn't perform so well. But maybe that gets the award for most resources consumed. So I don't know. If you think you're not going to win, then maybe try something crazy, shoot the moon, as they say. You'll get full credit for entering, and we would be interested in these systems. I think you're on your own now, so is there anything we should say about how people can connect with TAs if they're remote?
I think they can just call in.
Okay, just call in, and there's some details on Piazza, right?
Yeah.
Okay. We're available. Great. Get to work, I guess.